Hi everyone, my name is Jaime Zendejas. I'm part of the American team and I will be presenting on apples and oranges, the radio question. So, as a quick introduction, the prompt gave us the question about building a simple radio out of fruits and vegetables, with the immediately given example being a potato. And so we can start by first, before we discuss the process of building it out of a potato, we can discuss just AM radio basics. So when we want to transmit a radio wave through specifically amplitude modulation, we'll take the message signal and we'll double it over and flip it, and we'll take a carrier signal at some specified frequency that's constant, and we'll run it through the sort of wave packet of the doubled and flipped message signal, so that now this constant frequency wave carries all of the information that the message signal did originally. Now, a simple representation of an AM radio circuit would typically contain a capacitor, some form of inductor, a diode, an earpiece, and an antenna, with each having specific roles in this, the capacitor being a low-pass filter, the diode being the wave rectifier, and the air coil, or the inductor in general, helping to tune to some resonant frequency that we would want to listen to. And obviously the earpiece would make the noise and the antenna actually receive the radio waves. So when we examine the circuit that's kind of shown in the prompt example, we can build a sort of estimation of what this circuit diagram should look like, and we see that the capacitor and diode are in parallel, and there's no presence of an inductor here. So immediately this seems a bit strange, because if we want a well-working AM radio or some kind of radio, we want to be able to select for frequency, and without any way of doing that, it's not a very good radio. So we have a large bandwidth, no selectivity, and in general, because there's no supply to this kind of this circuit, it's going to have a very weak pickup from the sound from just the antenna, unless you go through extreme processes of massive lengths of wire and such. But maybe we're looking at the potato diagram wrong, and there's a better way of actually examining this. So we can look at the characterization of a potato or any other vegetable or fruit, whatnot, and look at some of the factors that are involved inside of it. For example, many fruits and vegetables have a high water content, making them naturally conductive. Then, because their water content is conductive and they have cellular structure, the cellular walls causes like a sort of dielectric between the conductive parts of the water, creating many little capacitors all throughout the vegetation. As well, because of more of the complex cellular structure, the large molecules present in any sort of vegetation, that's going to lead to resistive qualities in your vegetable or fruit. And the complex cellular pathways, like from a cytoskeleton or so on, that are inside of any of these things in order to like transport nutrients directly to specific portions of the organism, that can lead to extremely random or like curved pathways that the ions will flow in that can lead to some amount of inductance. So, given all of that, it's possible that rather than considering it just as a capacitor or just as a resistor or somewhat, you can consider it to be a small self-contained RLC circuit. Now, if that is the case, we would think that any kind of RLC circuit should have some characteristic frequency response to it. So that's where we wanted to begin. We wanted to try and see if we could find something like that and move in that direction. So in order to do that, in order to get a good signal, in order to see all of this, we hooked up the potato. We threw out the dielectric that goes in between chopping it. You can see in the photo that it's there, but the wires are connected on one end. We're just looking at a whole potato, essentially. We hooked a signal generator straight to that and pumped in a 5-volt sine wave at multiple different frequencies. And we connected it in series with the potato, then to the diode, and then in parallel we had an oscilloscope and the earpiece to see what we were getting, to make sure it was properly demodulating the wave that the signal generator was producing, and that the earpiece did in fact pick up a tone. So upon doing so, we scanned through a frequency span of about 100 kilohertz to 20,000 kilohertz, and we found that in both a potato and a lime, there was in fact a very sharp resonance frequency. And so this kind of reinforces the idea that this is indeed some form of RLC circuit, because it has not just a sharp peak at a specific frequency, but the narrow bandwidth implying a smaller Q factor means that the resistance and the capacitance are in a good proportionality with the inductance to produce this kind of behavior rather than being an extremely noisy, large bandwidth kind of radio. So that's kind of, okay, maybe we do have an RLC circuit self-contained in each of these potatoes. So the next thing we could do is we can take a Cauchy distribution fit, and then we can, from that specifically, determine the Q factor analytically. And using that and a simple measurement of resistance with a multimeter, we can then derive out what the relevant inductance and capacitance values of any sort of vegetable that you're going to put in this radio to be. And then now that you have all of the relevant parameters, you've essentially characterized your vegetation as its Thevenin equivalent circuit of an RLC. And with that characterization, we are able to then move on to actually improving the radio, trying to get that high audio fidelity that we want, seeing what we can do. So now that we know, like, okay, it's just the small little RLC circuit, improving it to get higher audio fidelity, to select for bandwidth and such, they're just the straightforward calculations that you would do for any other circuit. You just figure out what resistances, what extra inductances and capacitors you might want to zone in on specific resonance frequencies when you want to tune. And then specifically when we're talking about picking for an optimal fruit that would produce the best quality, it's kind of difficult because for the most part a lot of them are going to be similar. We can say that if, depending on what characteristics you want in your radio, you would pick different fruit. As well, there could be some more overtoned characteristics you might want, like you want a higher capacitance to inductance ratio because of like reduction of noise and such. But in general, the characteristic is going to depend on what you want out of your radio rather than just one end-all, be-all fruit or vegetable that will do it for you. Looking at the circuit specifically, the previous circuit diagram given didn't actually have a way to tune for your frequency that you wanted. So a simple improvement upon this is adding a double coil kind of thing where the separation distance between these two can directly control the tuning and the audio fidelity of your AM radio. Essentially, you would have some kind of switch coming along this coil line, controlling the inductance and breaking it off at some like coil level, and the distance here controlling the amount of actual EMF you get from the mutual inductances when you receive a signal from your antenna. And of course, though, if you bring them closer together, because this isn't being tuned, you're going to get more noise. So you'll get louder and more, you'll get a louder signal, but it'll be less tuned to the exact resonant frequency. So there are some trade-offs with that, but that at least allows you to control for some of the parameters you want a little bit more. So in conclusion, we can consider all of the aforementioned information. There's unlikely a single fruit or vegetable that will do the job perfectly for you, but if you're willing to run some tests, you can find optimal ones for exactly what you want in your case and what you would need to then improve upon that. And while I haven't gone over it in massive detail, given that we can characterize it as an RLC circuit, it should be very possible to turn it into a transmitting radio that just has an RLC circuit somewhere in there. And maybe a few potato batteries would be in order. Thank you.
Okay, so hello, so my name is Mathieu Lisée, I'm from École Polytechnique, and I'm going to present our opposition on problem number 5, apples and oranges, which was presented by the US team. So I thank you for their presentation, and now I will move to the statement of the problem. So the problem statement is that we can make a simple radio from a potato. And in fact, we investigate that will the quality of the sound depend on the fruit and vegetables or other interesting parameters. So this is the question, and we're interested in what hypothetical plant could provide the best fidelity, and could we modify the setup to work as radio transmitter. So first, I will go for a quick summary of the presentation. So first, they tried to make the setup of the AM radio. They showed the setup in theoretical progression, and they make the equivalent circuit of the potato radio, and they show that something is missing. So the radio cannot be a simple wire. In fact, it does have a role, and they explain this. They show that they with biological arguments. In fact, they see that a potato could be well approached by an RLC circuit. And an RLC circuit is interesting because it has a resonance, so it will play a role on a frequency. So this is what we are here, and then they provide some experimental progression. So in fact, they will study the potato with a pretty nice frequency study that allows them to understand its behavior. Then they obtain the quality factor, and also they show that they do the same for lemon. And they also suggest that we could select frequencies by adding 2 coils into their circuit. So now, some strong and weak points. So first, there was this setup with the AM generator. Then the study of the experimental study of the frequency response, which I think was the most interesting thing in their presentation. Also the resonance and the Q factor, and some additions. So, however, there are some weak points I need to say. So there was no justification of AM radio choice. Why AM? Everybody uses FM today. Also, there was no dependency on geometrical parameters for the potato. So, what potato do you use? Is it humid? Is it large? Is it small? I don't understand. So maybe we could have studied the dependency of your frequency response on these parameters. Also, you proposed to tune the potato, but I did not really understand how you do it, and finally I thought that you were doing this with the additional coil, but I'm not really sure about this one. And also, yeah, the study of other fruits was pretty minimal, I believe. So finally, let's get back to the problem statement. A simple radio can be made even from a potato. So this was well attempted, I believe. The quality of the sound will depend on fruit and vegetable. I did not have a really good answer. I think there are many things missing. What hypothetical plant could provide high fidelity sound? No answer at all. And can the setup be modified in order for it to work as radio transmitter? I'm sorry, but you didn't answer. I don't remember maybe. Okay, and so I have some discussion points. So I will go from what you presented. So you show a quality factor, and on slide 9, you show curves where very sharp resonance, and then I think, okay, we have very sharp resonance, so maybe we could use this to select the frequencies in order to listen only to one radio station. So I would like to know what you believe of this, and this would give some elegance to the problem, I believe, with getting away the additional coils. Also, you say that we could. Yes, okay. So this leads us to the second question: how can we tune this without the coils? And also about this part of the problem, which I am not really satisfied with the answer, is what is the impact of the fruit choice or fidelity? Because on fidelity, so what is the impact on fidelity? Oh, sorry, I didn't see you. Sorry, I was thinking fidelity. I'm really sorry. Okay, yeah. Okay, so now I would like to move to discussion, if that's right.
Of course. So, starting at your first point, can we do frequency selection? Completely, yes. Because of the very sharp resonance peak,
Yes.
the potato naturally, without any secondary coils, will tune into that resonant frequency all on its own with the antenna as it is. Moving to your second
Oh,
point.
no, first, I'm not really, we're not over yet. Okay, so you say that you can use the very sharp resonance to select the frequencies?
Yes.
Okay, so can we go back to slide 9, or at least maybe you know the length of your resonance? What is the width, maybe? Okay, so if here this is frequency, and here is response, I call this A for amplitude, and we have something like this. Okay, from your measurement, and you calculate on the several sides the quality factor. And what I'm interested in is this sufficiently sharp to allow frequency selection for AM range?
Yes. So because the Q factor because the peak is as sharp as it is, we get only high amounts of voltage out of the resonance right around about 18. Actually, you bring up a very good point. No, it's not sufficient in the AM range. The resonant frequency that the potato will naturally fall around is about, I believe it was 18,600 kilohertz. So that's
18 kilohertz?
No, 18,600 kilohertz. So about 18.6 megahertz. So this is well above the AM range, which is indeed why I would put in the extra inducting coils in order to start to change and move away from the current resonance peak.
Okay, so in fact you calculate the quality factor, but anyway the resonance is not placed at the right frequency.
For the AM range, it's not currently placed at which is why.
Okay, so where would you hope? What would you hope to hear with this resonance?
See,
if it's not AM frequency,
you wouldn't hope to hear anything at this specific resonance, which is why at the end I would suggest that we build upon the original vegetation radio and add the other coils so that you can start to move the resonance peak elsewhere into the AM range.
Okay, thank you for your answer. I would just like to point out that in your presentation you show value for quality factor, and I believe it's even if you can shift the resonance, it will not at all be sufficient, because your quality factor, in fact, if here what I show is the AM range, you will have something like this, and in fact the resonance takes or maybe something like it's offsetted. But here, if you take if you compare Q to the width of the AM range, it's much too large. And in fact, you won't be able to select one proper station.
Even that can be accounted for with a double coil proposition.
Oh yeah, okay, but we're out of the problem. That's what I meant. Okay, so now I would like to talk about something else. You showed in your presentation that this is a potato and it has this behavior, and I would like to understand. You say that a cell, a biological cell, is an RLC circuit. Then I have a tendency to believe that you could, as all the components, we're talking about a linear, you could just sum up the cells and to build what you want for this capacitor, for this circuit. And you could just, in fact, I mean, like, select the geometrical parameters, maybe, to the right geometrical parameters, could give us...
Indeed, you can start to mess with the geometrical parameters of your potato in order to affect things like the capacitance, especially by, say, if you were to increase the surface area by chopping up your vegetable into various slices, maybe adding dielectrics between them, you can easily shift the factors inside of the vegetation on its own to mess with what values you get here. So if you're unable to get the actual like extra components, say the point of this was to build something simple, so maybe you can't.
And will you manage to go to AM range? Yes or no? By cutting the potato or choosing its shape?
Further investigation would be required to determine.
Okay, thank you very much. Okay, so now I would just like to move to my last point. Okay, so the main interest of the subject, I believe, of the problem is about the fidelity, because almost half of the sentence is about this. So in fact, what is the interest of the potato? What is its role on the fidelity?
So the potatoes, or any vegetable's role in the fidelity is going to essentially be how we define fidelity. One, low noise. So how clean of a signal can it produce?
Hello everyone, my name is André Juan, I'm from Team Brazil. Now I'm going to review the presentation. So first of all, thank you very much for both presenter and opposition. Let me just sum up everything you've done here. So about the presentation of the reporter, it was a very interesting presentation. You first of all told us a little bit more about the theory behind the working of a radio, and you mentioned the basic schematic circuit, which is very nice. But then it's a very important point captured by the opponent, because you only mentioned AM signal, AM radio, so why not FM? And we can further discuss on that, but it's nice that you at least mentioned something about AM. But then, well, you recognize very well that schematics we have for the potato, it enabled us to actually select the frequency, so how can it work as a radio after all? So it's nice you recognize that. And then you were able to notice that we have some electrical properties in our vegetable, in the potato, so that it can actually, well, be considered itself a RLC circuit. It has a resistance, a capacitor, an inductor, so it's very nice you recognize that. And then you notice that you can characterize this circuit, and actually you also notice that if you use different vegetables, it may be a good idea because you can have different configurations. And you notice that the limitations of your method, and by using the vegetable as a circuit itself. So it's nice about that. And of course, well, the bad thing here is that you really didn't show us any attempt of actually trying to make your radio work as a radio, because okay, you did some experiment, but you actually did not characterize your circuit with experiments and actual data. You did, okay, you obtained your quality factor, but what else? I mean, would you be able to characterize it a bit further? So the vegetal parameters were not very discussed. I mean, you mentioned that there are some parameters, but what are the actual influence? It was not mentioned. And you didn't mention at all about the distortion or hypothetical plan. So it's bad you didn't mention that. And of course, some faulty points, the opponents really did recognize those and guided a very good opposition on that sense. All of these I've just mentioned, you really said about this. But the thing is that in the remarks of the opponent, in the discussion you just had, you just focused on a very important and nice point, which is about the resonance frequency, and I think that's okay. We already understand that. But then there was no discussion at all about hypothetical plans. On possible experiments, okay, we didn't have experiments, but what can we do? And you really didn't touch on transmitter during the discussion. And that's exactly what I think we should do right now, is to go through these points we did not discuss and try to understand the problem a little bit better, okay? So the thing is, well, let's first start about sound quality. Those are the points, very important points in the problem. It's in the statement of the problem. So what is sound quality exactly, and how does it depend on a radio parameter in general and in the kind of a vegetable radio?
So certainly sound quality would be something we need to define beforehand.
Exactly.
I would define it as specifically the amount of noise that's picked up on your signal. So even if it's at a lower volume, so long as it's a clean sound, I would personally define that as high sound quality in this instance.
Okay. Do you agree? Yes. Maybe I can just propose a definition that we could use.
Okay, nice.
In fact, I think you talked about how you could select frequency in your presentation, but I think it would be interesting to separate this from the fidelity. So here is the. So you said you use AM modulation. So in fact, if you take an AM modulated signal, you will have something like this, and I take only one frequency, okay? So like this, we get away of the frequency selection problem. So we listen only to one frequency, and I think like this, it's much easier to define the fidelity. And we say, okay, I send in a modulated signal.
Okay.
The radio, its job is just to make it audible. Like, for example, I don't know, okay, we can hear it. And so I think it would be more interesting to study the fidelity only on this one frequency signal.
Quality is also important, and the thing is that now we talked about fidelity, it's about the hypothetical plant. It mentions, okay, if you can actually make a hypothetical vegetable to work as a radio, how would
So certainly a hypothetical plant that could be used to produce a nicer radio, considering the different. What?
How exactly?
So considering the various factors that I had brought up earlier, based on like the conductivity of the water, the resistance due to cellular structure, the inductance due to cellular capacitance and inductance due to cellular structure. We know that we would want for better frequency selection, we would want a higher capacitance to inductance ratio. So we would want to pick something that has a lack of, say, cytoskeletal structure and a high water concentration. This would reduce the inductance and increase the capacitance. A fruit that could do that pretty well would probably be an orange. It has these little pellets of juice, essentially. They can all act as tiny little capacitors, and because of the lack of like a very fine inner structure, the inductance would be much lower than, say, on a potato, which is a solid mass all throughout.
Okay, now, do you agree with that?
Okay, so what you propose is that you use you use the fruit that will have the sharpest resonance. Am I correct?
Yeah.
That
it doesn't solve a problem, right?
Yeah,
It's
okay,
still
but
just
you still have the problem of the offset right here.
Yeah.
And we still have several order of magnitudes of difference.
Exactly.
So the offset can easily be solved by the introduction of the double coils at the end of the.
Yeah, okay, but
so all that would be required is a few pieces of metal that you could find around. The whole idea.
few metals.
Like the coil.
Okay.
Yes.
We keep it simple.
The main idea of
I think that's great. Now about the transmitter, I mean, at least theoretically, what could you change in order to make it work as a transmitter? Just try to elaborate on that.
So to make it a transmitter, we know that the vegetation itself will act as an RLC circuit. Plenty of transmitters already have these in them, so you would just need the standard circuit diagram for one that contains one, and the addition of, say, some form of crystal oscillator that can actually produce the frequencies you're trying to transmit.
All right, you think so?
Yeah, on this one I kind of agree with the reporter, because I believe that you will need a non-linear component for transmission, or at least you won't be able to do this only with linear components. I mean by linear components, fruits and RLC circuits.
Yeah.
So I think that you will need to add some transistor or at least non-linear components.
Oh, okay. So that's interesting you mentioned that, because in your discussion you really, in your conception, your hypothesis that your vegetable is itself it works as components, all right? So could you have possibly a transistor or a diode maybe in your vegetable itself?
It would be far more unlikely to develop a nonlinear electric component from the vegetation. So I do agree that we would need to add, say, a transistor, like you said, in order to create a transmitting radio.
Okay.
As well as, of course.
But it's difficult to do naturally, you mean. Okay, let's go to the questions, please, to the reporting thing.
So you say a main issue in trying to get a good fidelity, or one of the issues, is that the frequency is far off from AM range. But that is not necessarily a bad thing, simply because the expected frequency range is not in what we currently define as AM, does not mean it works any less well as an AM radio. The amplitude modulation can work equally well in many frequencies beyond just the ones we currently use for AM modulation. That is a government mandated section, not anything that is particularly well suited for AM modulation. A radio that works at this frequency with AM modulation is just as equally a radio as any other radio.
Okay. Well, I think that's an interesting answer. But the only problem is that you won't be able to listen to radio. But
exactly.
It's not quite radio stations that emit at that frequency.
In many cases, these kinds of simple radios are often used for, say, military purpose. So possibly the radio station you would want to tune into may not be something broadcasted publicly. So like the foxhole radio could be used better at a very unique, unused frequency.
Okay, so please.
I did get that you started with the IM regulations. This is for the get IM. And we have assumption that we suppose that we have frequency selection. So we have our good frequency selection. How from frequency selection, this IM modulation, how can we get the signal, how we can get audio, and how the fidelity of this all this transformation will depend on potato. It will depend a lot.
Right, so I believe I've answered. So the sound quality obviously will depend on the actual characterization of your potato. You know, so the standard, like the hole, the size of it, the geometry that you select for. You know, how you cut it up. You know, all these things, the type of vegetation you pick. You know, it's actual biological.
Just I will precise the question. I usually looking for a France blue. I don't know. I just listen it, and I want to listen it, and I have just one potato. And what potato I need to listen it, and what do I need more for just listen to it?
Yeah, I think his questions. I think that his questions is about how do you make from amplitude modulated signals that the radio is broadcasting. How do you make something you can hear?
Yeah.
What is required for this? You have the potato. What else do you need? What
To make it a radio.
yes.
So
To listen.
all you need is the components shown in the circuit diagram to
Yes,
make it produce a noise. Just flat out make it produce a noise. All you need is the potato, an antenna.
Okay, what does that mean, a
diode.
noise? Do you consider it that it's demodulated already or not?
Yes, demodulated.
Okay,
So
how
you
do you
need
know
to-
that it is demodulated?
So the diode functions as the not the diode only. The diode plus the capacitance of the vegetation act as a rectifying agent, and then a
Oh, yes.
low pass filter.
Okay,
which-
could you draw it maybe on this roll, or I can help you.
So when it passes through the diode, when the diode takes it, it essentially takes off any negative signal. So
Yes,
then you just
okay.
get the top parts. Then when it goes through any sort of capacitive function, it'll low pass filter it. So all these high frequency kind of bumps will smooth out back to your original
Okay,
message signal.
so you say that in fact this is the capacitance that will define how this smoothing is done.
Yeah.
Yeah, if I understand well. Okay, so this capacitance is in the vegetable.
Yeah, it's exterior, right?
So
I mean,
if you are able to demodulate this properly, it is because your vegetable is appropriate. So in fact, it has a high quality, high fidelity.
Yes.
Am I correct?
Yes.
So in fact, no, it's just what you said. In fact, no, you need the capacitance to demodulate.
Yes.
So in fact,
Of course.
you have a new condition on your vegetable.
The capacitance is contained within the vegetable. That was
Yes.
Should we move on to the concluding remarks of the I have a question to the reporter. So going back to your circuit where you measure the resonance of the potato, so do you think that the technique of connection that you use, so just loose wires and alligator clips, are suitable for the tens of megahertz frequency range that you are aiming to?
It may not be perfectly suitable.
Yeah.
This is why I would have preferred to run more tests with better equipment. Unfortunately, the equipment was not readily available, and I didn't want to go overboard with like higher precision things, because you wouldn't be able to do that in the concept of what this question is asking us. You know, it's supposed to be very, very piecewise, very broken, and kind of what do you have, what can you assemble.
Yeah.
Do you think that the RLC properties of the potatoes vary in time after you cut it?
Definitely. Especially if you cut it, by exposing the inner portions, it'll start to dry out. And as I mentioned before, the liquid content is what gives any of the vegetation its high capacitance, or not capacitance, its high conductance. So if it starts to dry out, it will definitely start to lose that conductivity and lose all of its, it'll degrade the RLC circuit of sorts.
That's a question. At a certain point, you claimed that about the orange. What is the difference with the lime?
So between the orange and the lime, there isn't very much of a difference. That's why just a moment ago I preferred to say citrus fruits in general, because indeed, you're right, there's not a huge difference between an orange and a lime, aside maybe the volume
Maybe
of
I
it.
was wrong. It seemed to me that you were saying this could be a solution, so you tested the lime, so what was the real difference between the two?
In practicality, the real difference was that I saw the lime in the grocery store first. However, in general, there can be a difference based on the volume of the fruits, since limes are typically much smaller than oranges. exactly, the geometry will affect it, and so based on that, the orange may be better for its higher volume, so it should have a higher capacitance than the lime would.
You were supporting the fact that in orange you have these little vesicles or quarters of the orange that could behave like capacitance, and then are you sure of that?
Based on simple knowledge of
I would ask you in that way. Do you think that those parts are the conductive part that behave like the metal plate with capacitor?
the liquid between the actual like walls of the little pods would act as the metal plates because they're the conductive material, while the pod wall, the pellet wall, that would act as a dielectric between the liquid pockets.
Yes, actually I have a question to the reviewer and the opponent. So you accused the reporter of not considering the FM radio receiver. So do you know some simple circuit for the FM demodulator, which is of comparable complexity to the one proposed in the
No, okay, thank you for your question. In fact, my criticism was only that he did not explain why he chose AM radio.
Yeah, because my impression was that you expected that
No,
you
no.
would build the FM.
Oh no! Of course not. Of course not.
Okay.
We had we made the same choice. In fact, but in fact, FM demodulation is very much more
Yeah, you use
complicated.
the local oscillator and stuff like that. So this is not simple. thing.
Yes. No, of course.
So-
No, I didn't dwell on this.